Now, this idea of playing around with the field brought us to something, to a different one. It's the composite extension finite field over low overhead network coding, the telescopic codes. The idea came when we started with this sparsity, right? We said, okay, the sparsity is good for complexity. And then to the end, we got, when we looked into when are the duplicates are coming, it was always to the end. And we said, we even made a patent out of it, we said, why don't we just change the density towards the end? So where we have the risk of being linear dependent, we increase the density of the code. And that helped. And we said, we called it shifting gear density. And then we had the idea, why not shifting the field? So it came from these two plots that you should know by now. The left is this one. The binary code was very bad. This is this 1.6 extra packet per generation. Okay? Not good. But complexity-wise, very good. And the other one that is good in the performance of the code had very high complexity values, and there was decoding. Why could we not combine that? And if you remember this plot, number of linear dependent packets between each ring increased. This is the generation size of 16 packets. And the green ones are here the probability that the packet is not usable. So in the beginning, everything was usable, and the risk of being not usable was high here. Only in the end. And the question is, why don't we use one field in the beginning, and then we end up with a different field? Can we do this? It works if we could somehow change the one field into another field. Okay, then let's just do it. There's some pattern on that, as you can see, called intrinsic information conveyance in network coding that was together with Nokia. Then we have more on Fulcrum. Daniel Lucani was working on this with us. Very interesting. So what we want to do now is, can we have fields that where one field is part of another field, so to speak? Now let's look into the field 2 to the power of 2, the multiplication table. We had this before, right? We used it for our coding of the packets. So then you have 4 elements, and you say, can I code this? 0 you don't need, and then you say, this is the result. And if I take a higher field, 2 to the 4, the question is this field part of this field? Then we would be done, but it's not, right? Where this 2 by 2 is a 3, here is 2 by 2 is a 4. So it's not inherently given that one binary extension field is part of the other one. So what can we do? You change this field by something different, which is then, this is 2 to the 2, as before, this one here, 2 to the 2 again, and now we do 2 to the 2 to the 2, which, this is PowerPoint, they don't, LaTeX would have done it, right? But here we want 2 to the 2 to the 2, which is also 16, right? But it has a different mathematical interpretation, and now suddenly 2 by 2 is 3. Okay? It's one trick. Here's the way how you calculate on that. It's quite interesting. But what we want to do now, once this is working, this matrix, we just say, okay, let's take packet 1, 2, 3, 4, and 5. And we create a coded packet by having 3 packets in a, this is just binary, then 2 to the 2, and this is 2 to the 4. Okay? So look at the encoding vector. Even the encoding vector is shrinking with that. Okay, for these, you have very fast encoding, for example. You can have now, on the decoder side, you can clean up. What you do is, if you get the coded packets like this, first you clean up the binary part, right? And then you go to the middle part, and later you clean up the rest, right? That is one by one. You treat them in a way that you first have the binary matrix here, then the 2 to the 2, and then 2 to the 4. And you can then look, what is the total overhead for a certain generation size. As I told you, the encoding vector now gets down, but more interesting for us is what is the distribution? So how many of the binary, how many 2 to the 2 should we take in? And here is the optimal choice of field distribution over the generation size. So this is 100%, right? So when your generation size is huge, like 512 packets, I don't know any application that would do that, but just to, then most of the packets are binary, and there's maybe the last 4 packets, who cares, right, are in higher field. But let's go where 32 is. That could be a good application way. Then you know that more or less 75% is binary. Then you have 10% 2 to the 2, 5% 2 to the 4, and a little part 3% maybe 2 to the 3. I don't know if this ends up in 100, but I hope so. But you see, this will go 16, only 40% binary, 40% 2 to the 2, and so on. And the very high fields you only need for very low generations, right? You don't want to risk. So therefore, if you have here 5, I think it's generation of 5, you only have 2 to the 4, 2 to the 8, 2 to the 16. Okay? So now it's another trick, right? What we do is always think about how to get either the complexity down, how to get the latency down, how to get the coding speed up, which is energy related later on. So we always work with this. But in the end, what we want to have is resilient communication. And if you have heard about this term ultra low latency resilient communication, everybody looks for a solution for that. This is one of the ways how you can do it. You get both latency and resilience under control. This is what it does. Here are some examples what you do. Also, just to say when you have 512 packets, yeah, the 1.6 extra packets per over 512 packets is marginal. Therefore, they don't care about this, right? And then the more you move into this, you always move to higher fields. Okay, so these two things, fulcrum as well as telescopic, very nice way to really think about a overhead and complexity, heterogeneity. I think that is what I like so much on the fulcrum code, that you really try to understand it from the network perspective. That you do it not end-to-end. Telescopic is, for example, more or less end-to-end. We did not even look into recoding. This could be a nice research topic. But the fulcrum is really looking into network constraints like complexity. That's awesome, right?